My name is Tobi, and I'll be talking to you today about fast JVM startup using Checkpoint and Restore. So a little bit about myself. I'm a developer on the OpenJ9 team at IBM. My main focus is on the runtimes part of the JVM. For those who don't know what OpenJ9 OpenJ9 is basically the open source version of the IBM SDK. And now there's a downstream product called CRIU, so same thing. CRIU is just a branded name, but it's all based on OpenJ9. So today I want to talk about a few things. First of all, I'm going to motivate why we need fast startup. Perhaps some of you already know, but I'll go through that anyways. So we'll look at why that matters. Next, we'll look at some of the existing techniques to improve startup time. So it'll be mostly a review. Then we'll look at CRIU. I'll describe what it is and how you can use it for Checkpoint Restore and how that's an alternative approach. And then we'll take a look at how CRIU is used with OpenJ9 to improve startup performance. And then lastly, we'll look at some of the challenges associated with this approach. All right. So why does fast startup matter? In order to answer this question, we'll first take a look at how applications are being run today. So in the last 10 years or so, there's an increasing trend to deploy more applications to cloud environments. In many cases, people are using public clouds like AWS, Azure, etc. These have benefits as you can decouple the task of maintaining infrastructure and all that stuff and just focus on writing code and then pushing it out. Someone else can worry about managing hardware and networks and all that stuff. So the general consensus is that this is a beneficial approach, and it's one that a lot of people are moving towards. The main costs cloud vendors incur are networking, storage, and compute costs. And for network storage, it's the cost of hardware, buying the hardware, maintaining it. For the purposes of this discussion, I'm mostly focused on the compute costs. So that's CPU, RAM, and the power cost of maintaining those machines. Typically, the way pricing is done is it's done on a pay-as-you-go type of model where you pay for a certain amount of CPUs, RAM, multiplied by the amount of time you use it. So for a lot of applications out there, demand isn't constant. It varies over time. You may have peak loads during certain times of the day, certain weeks of the month, certain months of the year. And in other times, it's not very high. So using a deployment strategy that can scale as your demand goes up and scale down as demand goes down is really a way to save on resources. And lots of people are adopting this approach. There's technologies like Knative, OpenFAS, which make this easy to use. So scale to zero is a great way of minimizing your costs. So while scale to zero is very good, to use it effectively, you really need startup time to be well under a second. And that's because a lot of applications are very sensitive to latency. This is typically true for end user applications, things like e-commerce, streaming, etc. So if you're hosting an application with a JVM-based app server, then the latency cost is proportional to the JVM startup time. And so every time you spin up new instances, you start up the JVM and etc. So you can see how the JVM startup time is a part of the latency cost. And this is why JVM startup is very important. And minimizing startup time can greatly improve your experience in the cloud. Okay, so now that we know why we need fast startup time, we'll take a look at ways that have been used in the past, present, to improve startup time. And we'll talk about some of the solutions, look at some of the trade-offs. Yeah, so the first approach is basically class metadata caching. And this is an approach, well, I'll take a step back. When the JVM loads classes, loads a class file, it generates some metadata to build an internal structure that represents the class. And then it uses that to actually run the code. So with class metadata caching, the idea is that you save that internal state. And instead of going through that process again on subsequent run, you just start from that intermediate state, and you have a much faster path to when the application's ready. There's a few ways of doing this. John talked about AppCDS earlier. OpenJ9, we use shared class cache. Essentially, this is an approach where you can save typically the way we use it is we save the static portions of the class. So things like the bytecodes, string literals, AOT compilation, and we persist that data. And then on a subsequent run, we map that data in, and instead of loading and reconstructing all of that again, we just use what's already there. So the benefits of this approach is that it's probably the easiest way to get a start boost. With OpenJ9, you just turn on an option and it works. If you're doing complicated things with a custom class loader, there's some cases where you do need some code changes, but for most applications, there are no code changes involved, and if there are, it's fairly trivial. And the nice thing is that at the end of the day, it's still a JVM, so it's exactly the JVM you're used to, and no changes there. The drawbacks is that the startup gains are fairly modest in comparison to some of the other approaches I will talk about. So you can get under 900 milliseconds for Liberty ping perf. But typically for small applications, you can see roughly 50% startup improvements. Okay, so another approach is to statically compile the application. So as we heard earlier, a big chunk of startup time is taken by loading classes, running static initializers, etc. It's actually a big reason why a startup time is very slow in the JVM. And by statically compiling, you can avoid all of these costs. As Christian Weimer spoke earlier about native image, it's a great way to really boost startup performance. So the benefits of this approach is that the application starts up very fast. With some examples on Quarkus, we've seen under 90 milliseconds. Another benefit is that because it's doing a closed world analysis, you can really strip out the parts of the application you don't need. So this footprint is very small, and the footprint in general tends to be a little smaller. Some of the drawbacks are actually related to the benefits. Is that with closed world analysis, it places restrictions on some of the dynamic things the JVM can do, and certain limits on class loading you kind of have to know ahead of time. Likewise with reflection. So this likely means that if you're trying to support an existing application, you may have to do a bunch of rewriting, and if you do depend on these capabilities, then your application may not work with this approach. And you also have to make sure your dependencies also work as well. So this is it's an approach that's usually better suited for newer applications. Because you are compiling an application, it tends to have longer build times, and there are some limitations in terms of peak performance. You don't have that recompilation as you do in a typical JVM, and so that does affect it. Okay, so the third approach is checkpoint restore, and that's what I'm going to focus on today. So essentially, the JVM is run, and then you checkpoint it at some point before the application is ready, but after you've done a substantial amount of initialization, and then you restore the application, and most likely in a different environment. So the savings are that you skip the whole startup phase, and you just basically resume the application. So the benefits are that you can get very fast startup times, much faster than what you typically get with class metadata caching. Not as fast as static compilation, but you can get fairly close. Because it is a JVM, there's no restriction on the dynamic capabilities. You use the same tools as you normally would with it. There is a JIT in there, so there's no impact to peak performance. The drawbacks are that it is larger on disk than native image because you are keeping everything, and it does require code changes. But as you'll see later, we're hopeful that this is actually very minimal, and that it's easier for existing applications to migrate. So the goal of this approach is basically to achieve something in between class metadata caching and static compilation. So we want startup time to be as close to static compilation as possible, but we want it to be as usable as possible for existing applications. We don't want to sacrifice anything if possible. Okay, so in order to checkpoint a JVM, we need a mechanism that can basically take the state of a live JVM, suspend it, serialize it, and then resume it at a later time. We actually did some experiments in the JVM level with this, but there's a considerable amount of work that is required to track OS resources, and we felt like this is really just a better, it's a problem that's better suited at with a tool that's at the OS level and has access to kernel specifics. So instead, we decided we'll try with CRIU and see how that goes. So CRIU stands for Checkpoint and Restore in Userspace. So CRIU is a project that began officially in 2012, but it actually started earlier, around 2005, under a different name. At that point, the earlier project was Checkpoint Restore in kernel, but then in 2012, the redesign happened, and they moved it to Userspace. So it's essentially a utility that can take a running container or a process and checkpoint its state and serialize it to disk. And then the serialized state includes everything needed to resume it at a later time. The saved state can then be used to restore the application exactly as it was at the time of checkpoints. So it's essentially freezing it and then resuming. So how does it actually work? So an application use many operating system resources like files, memory, shared, private, virtual, etc. Interact with control groups, namespaces. So at checkpoint time, CRIU queries the kernel for all OS resources that the process has acquired and is using in order to determine the state of the application. So it uses system calls like ptrace to integrate the process, to gain control of the process, netlink to obtain networking, to obtain the networking state. And then it basically writes all of that information out to file or files. And then at restore time, it replaces system calls used to create that original state and then maps back the memory, register values, etc., and resumes the application. So it's a bit of a simplification, but it's on a high level, that's kind of how it works. So at OpenJ9, we have a feature called CRIUSupport, which basically enables Java users to get access to CRIU. So it takes advantage of the CRIU capabilities from Java code, offers an API, and you just need to have libcru on the machine. It does a bit more than just call things in CRIU, as you'll see later. We've added a lot of functionality to make it easier to migrate existing Java applications to this model. And so there's a lot of JVM support to kind of smooth over the challenges that may arise. We've also added some functionality like diagnostic support, some performance tuning knobs, just to make it more like the typical JVM experience. This API is still work in progress, So things are subject to change, but overall, I think it kind of shows you generally how it works. As you can see, it's fairly simple. We've gone with something very rudimentary because we still want to get a better understanding of the problem space before we build it up. It uses a builder pattern to set up the CRIUSupport instance. And then the methods there at the top are just to query whether it's CRIUSupported on the machine or not. There are two methods there, and I'll explain why both are needed later. And then at the bottom, these methods basically modify how the checkpoint is taken. For the most part, they're a one-to-one mapping with the CRIU API. And then in the middle, these are methods to leverage JVM supports for things like hooks, etc. This is where most of the challenge is, and consequently, this is where we've spent most of our development time on. Getting this right is really the key to making this approach successful, and I'll go over this in more detail later. And then at the top is checkpoint JVM, and that's how a checkpoint is initiated. So taking a step back, in a typical workflow, you have the build phase. So this is compiling, linking the application, and then at runtime, the app starts. So you have the JVM startup, includes loading JVM, loading shared libraries, etc. Initializing the core JCL, initializing those classes, and then initializing the application classes. And then after all of that, the application is ready to run. And so there's a visual representation of what occurs, and these boxes aren't to scale. So what we're trying to do, the goal here is basically to move as much of that app starting phase into the build phase as possible. And so basically we want to create as short a path as possible to when the application is running. And that's how you get your startup improvements. So here's how you'd use the API. In your build phase, this would be similar to compiling a stock image or doing a cold run with shared class cache. You'd run your application as you normally would, and then a checkpoint would occur. This would be, our approach is to do it at a predetermined point. We don't do any asynchronous type of approaches. And then once the checkpoint image is created, the image will be saved, and then that's what you would use at runtime. And so at runtime, you just resume the image, and then you just you pick up what you left off. And this is how you get the performance gains. So you can see there's a much shorter path to getting the application ready in comparison to the normal run. So really, the picture kind of looks like this. There is a small amount of time required to restore the image. Typically, this is a very small fraction of the amount of time it would have taken had you done the application startup. Right, so how is the checkpoint initiated? So CRIUSupport uses a self-dumping approach. So it means that the process initiates the dump. There's some other approaches. I know OpenJDK Crack is doing a more asynchronous style. We haven't really experimented with that approach. We've kind of gone with this approach. Okay, so I'll show you how this works in practice. All right. So I've made a toy application here. It's going to simulate loading classes with sleeps, and then it's going to say ready when it's ready. So we'll compile that. Okay, so no surprises there. It's doing exactly what it's supposed to, and let's just time that. Okay, so roughly 3 seconds, and that was intended. So now what we'll do is we'll take a checkpoint right after it's done the class loading and initialization. So this is just the helper call, and what it's doing is it's calling, it's checking to see if CRIUsupport is enabled. If it is, it's going to create a checkpoint in this directory. We're going to tell it to not continue running after making the checkpoint. We need to tell it that it is a shell job. It's a way of letting CRIU know that you're launching an application as part of the shell process tree, so it knows how to properly restore it. The JVM implicitly uses file lock, so you also have to inform CRIU of that, and then the rest is just logging, and then it takes a checkpoint. Okay, and then we'll run it. Okay, so the message here is just, it's a message from CRIU just saying it's killed the process, and the checkpoint image has been taken. And then we'll restore the image. And you can see here, it came back in like 69 milliseconds. So it's roughly around the 60, 70 range. But that's basically how it works. So yeah, so this was a fairly toy application. So we'll try with something a little more real. So we've been working with the Liberty team to incorporate this feature. Liberty is app server. You think of Tomcat, it's kind of like an equivalent. And so we've added support in Liberty to make use of this feature to improve startup time. So we'll do a normal run just to see how it performs on this machine. Okay, so it took about 3.39 seconds. So now what we'll try with CRIUsupport, and I'll just show you what's being done differently. So the only thing, so a normal Liberty run will do all the steps above. It will, it's basically moving all the files you need for your app server over to the container, and then configuring it, and that's just doing a cold run, just warming up the shared class cache so that we can do AOT compiles and then build up the cache. The only thing different about this run is this last step here, and that's we're going to start up the server, take a checkpoint after application initialization, save that image, and then we'll commit the container image, and then we can restore it for improved start time. So let's give that a go. Okay. So it took about 300 milliseconds. Another go. 175. Typically, it's around the 170, 180 range. So you can see it's over 10x improvements, and that's the kind of performance gains that you can get with this approach. Okay, let's go back. So here are some perf numbers. These are some runs I did earlier. With ping perf, you can see it's a bit over like 15x. With Acme microservices, it's a little more involved application. Also a bit over 10x. Arguably, a better metric is first response time, and you can see there it's still, you're roughly at the 10x improvement range. Okay, so so that seems pretty easy. All we did is save it and then restore it. So you might be wondering why is this? What else is there in this talk? So there are some challenges with this approach, and that's what I'm going to focus on next. And you'll see that it isn't actually that straightforward. So CRIU lets you take a checkpoint and restore it on the same machine or on a different machine. And most likely it's going to be on a different machine because you're going to be deploying this somewhere else. So this is a very powerful tool, but there are consequences associated with this approach. The main consequence is that the environment in which the checkpoint is taken most likely won't exactly match the environment that the JVM is restored in. So, for example, if you take your checkpoints at 10 a.m. and restore it at 11 a.m., and you've got objects in your heap that are sensitive to time changes, this may affect your application behavior if you have algorithms that are depending on certain guarantees there. The challenges are, so we looked at restoring it at a different time, but if you restore it on a different machine, the challenges are even greater. The physical resources on the machine may be different. Things like CPU counts or memory may not match on the other machine, and these may have adverse effects in the restore environment. There's also potentially networking challenges related to restoring on a different machine. Anything that caches hostname, for example, may not function properly if the restore environment changes. So this is why it's important to have JVM support when taking checkpoints. And we believe that the JVM is best positioned to smooth out these differences and make the restore behavior behave more properly and as intended. Without some support in the JVM, it's likely your application wouldn't work as you intend or may not work at all. And so it's important to have support in the JVM for this. So in the previous slide, we looked at things that change in the environment. Here, we're more concerned about things that do not change in the JVM. So there are certain algorithms that rely on randomness, entropy, to function properly. These are often associated with security algorithms. So examples are secure random with a seed value in it. If you create a checkpoint and restore it multiple times, if you have that same seed baked into your image, that could be a security vulnerability. So it's important to provide a certain amount of uniqueness when restoring the JVM. So I've outlined a few problems, and these basically motivate the need to have a mechanism to compensate for the differences between checkpoint and restore. So essentially the goal is to enable a restored program to behave in the new environment as if it were started there originally. We want to make it work as much as possible as a typical JVM run. So essentially we need to provide a way to bridge between checkpoint and restore environments to kind of smooth out these differences and make it behave as intended. So to achieve this is one main requirement. We basically need a way to patch the state after restore and possibly pre-restore as well in certain cases. And then we want to do as many of those patches automatically as possible. As I said earlier, we want to lower the barrier for existing applications to make use of this. And so the more the JVM can do, the less the application has to do to leverage this. So with CRIUSupport, we do provide some standard hooks. So things like fixing up time-related APIs, so things like JVM timers and system nanotime. MX beans that detect OS resources, clearing DNS cache, adding entropy for security and random instances, etc. And some things we do are also for performance. So pre-checkpoint, we'll do a full compact to shrink the heap, release some pages that aren't used, just to minimize the size of the image. And there's some other enhancements we're working on in this area. We want to do a bit more static analysis at the time of checkpoints, do some more pre-compilation just to make sure that performance is optimal at the time of restore. So ideally, we could handle everything in the JDK, but the reality is that there's always going to be a need for users to add their own compensations as well. And so we do provide a mechanism for that, as we'll see later. But essentially, the way compensations work in CRIUSupport is we have a hook mechanism. And essentially, hooks are run before checkpoint and after restore. And the way it works is the JVM, when a checkpoint's initiated, the JVM will halt all application threads, and then it will run the hooks in a single thread fashion. And these could be to close certain OS resources, file sockets, file handles and sockets. And then perhaps record all the instances that you want to fix up on restore. And then once the restore is initiated, the JVM can fix up all the things in a single threaded fashion. And we do that for certain things. And then after that, all the application threads are resumed. So for the cases where we can't provide all the support that users need, the users can participate in this process as well. And so there might be some data that only the application developer knows about. For these cases, we can provide hooks so that users can do their own fix-ups. So these hooks run along with the JVM hooks, although they will be the first to run at checkpoint and the last to run at restore. So essentially, these are the lower priority hooks. And yeah, so there's the API there that kind of describes how that works. So as you saw earlier, the hooks are run in single-threaded mode. This means that you can do global state changes and not have to worry about any synchronization issues or race conditions. However, this does introduce a challenge. Some of the hooks in the JVM are Java hooks. And so the issue is if you are running code and you attempt to acquire a resource that's held by a thread that's currently halted, then you're in a deadlock scenario. So to address this, the JVM will simply throw an exception when this occurs. Likewise, if your hook attempts to do a terminally or indefinitely blocking operation, the same kind of exception is thrown. But there's some cases where you're in a situation where this has to happen. You may need to acquire a container resource. So we've introduced an annotation called not checkpoint safe, which can be applied to a method. And essentially what this does is, before taking a checkpoint, we'll scan all the thread stacks. And if we see a method with this annotation, we delay the checkpoint until that method's off the stack. So this is a way to work around container cases. But it's also a way to kind of eliminate the need for certain fix-ups. So if there's an operation where it's not really safe to take checkpoints in between, or it would be expensive to fix up in between, you can use this annotation to basically avoid that case entirely. It is an open question whether the single thread approach is worth it, at least for user hooks. Perhaps the users can just handle synchronization on their own. So that's something we're currently thinking about. That will likely add support for multi-threaded hooks anyways, but it is an open question whether it's worth the trouble for to ensure that you can do global state changes without worrying about synchronization. Right, so where to take a checkpoint? This is probably the most difficult question when using this approach. It's hard because the later you take a checkpoint, obviously the more sort of benefits you get. But and the reason you have more benefits is because you're running more of the application, so you have more code. But the challenge is that you're building up more state, and that means there's potentially more things to fix up on restore, and that's where the complexities arise. In our experience, we have found that when you're dealing with application frameworks, it's a simpler problem to solve. So in the example earlier with Liberty, there's only 2 positions an end user can select the checkpoints, and it's before application initialization. And that's in cases where you might want to, read from a database during app init, or after application initialization if you have a more simple initialization routine. So at the application framework, it's fairly easy, but if you're building this directly on the JVM, you kind of have to make the hard choices and decide what trade-offs you're willing to live with. So some of the other challenges are due to portability. So earlier I talked about how you can take a checkpoint in one environment, restore it in another. So the JVM has a JIT, as you all know, and this compiles and optimizes Java bytecodes. And to get optimal performance, you often you use the instructions available on the target machine. So you look at the machine capabilities to determine which instruction is the best. There's a possibility that you may take a checkpoint on a machine that has a higher level of capabilities and restore on one with a lower level of capabilities. And so because of this possibility, we have to be conservative during the checkpoint phase. So earlier in the example, you'd have seen that I added the flag to say that we are enabling checkpoints. This basically tells the JVM that this JVM, this live instance is going to be frozen and it might be restored somewhere else. So be very careful about what instructions you're using and make sure that it can apply more broadly. But we don't want to have to pay this cost all the time. So there is another option called CRIU restore non-portable. It's a bit of a mouthful, but essentially what this option says is that the JVM will only be restored at most once. And so this lets the JVM know that as soon as you restore, you look at the target machine, that is now what you're targeting. Feel free to use any features available on that machine. And so we only pay the costs at checkpoint, and at restore, when we do recompilations, we can make use of the host's capabilities. And the way to test if, in this case, at runtime is checkpoint allowed API that was shown earlier. So this mode is turned on by default. If you want to do multiple checkpoints, then you just turn it off, and then you can take multiple checkpoints. Now, the JVM is not the only component that kind of uses hardware-specific, the CPU-specific capabilities. Some standard C APIs also do this. Things like memcopy, memmove. They use instructions that are available on that host machine. So unfortunately, there's nothing we can do in the JVM to stop this, but there are some OS features that allow us to disable these optimizations or hardware-sensitive optimizations. So glibc tunables is enabled on, I think, glibc, I think it was introduced in 2.18, but there were some bug fixes in 2.24. So this basically disables these hardware-specific optimizations. Now, unlike the JVM, we can't fix this up post-restore, but in practice, we haven't really seen a noticeable perf impact to disabling these. So we talked about security a little earlier. So a lot of security services have state that you don't want to be serialized. So with standard APIs, it can be tricky or even impossible to serialize them. So with CRIUSupport, basically in the checkpoint phase, you are limited to only APIs that we have written specifically for this mode. So these are security services that participate in the checkpoint process. So when the checkpoint's initiated, they clean up their state, and then on restore, it reinitializes the state. Now, at the start of the talk, I talked about workloads moving to the cloud and how fast startup is very important in these environments. And so we want to make sure that you can actually use this thing in real world scenarios. CRIU uses system calls like ptrace, and historically these have required elevated privileges, things like sudo or capsysadmin. Most people don't want to have that turned on when they deploy. So as of Linux 5.9, there's a new capability that basically separates out everything needed for CRIU in one capability and leaves out the rest. So as of 5.9, you can use this capability to restore, to take checkpoint and restore. And it's the minimal set of capabilities you need. So it kind of minimizes your exposure from a security perspective. There are some platforms that recommend or require random EIDs. I think OCP is one example. So we have added some support in CRIU for handling these cases as well. So very quickly, so putting a live JVM instance in a container image makes it challenging to debug, and specializing an image for each target that you're going to fit for each environment that you're targeting at deployment is also burdensome. For example, if you've got nodes that are 1 gig and nodes that are 2 gigs, you don't want to have to make special images for these. So what we're doing is we're adding support to basically add JVM options on restore. So you build one image, but then on restore, you provide options that changes the JVM behavior. So you can add diagnostic options, turn on thread dumps, or and even use some tuning parameters. So the list for tuning parameters is fairly small right now, but we're adding more as we go on. So figuring out where to checkpoint can be tricky. Knowing what state to fix up is also challenging. And there's lots of stuff to package for this. So we find that this really works best, this approach works best with application servers. So things like Liberty, Spring Boot, that style of workload is really probably the best use case right now that we've seen. Similarly, we think that containers is kind of the best way to package everything together and put all the dependencies you require there. There might be other use cases, but so far we think this is where this approach works best. So as future work, we're looking to add more support in the JVM to enable more debugging capabilities. So we already have some for things like method tracing, thread dumps, and things like that. We would like to be able to enable Java debugging, like with a debugger on a restored image. So this is your regular production image, and then you can debug it as well. So there's a bit of work there required. Also, we want to add some options to modify heap geometry so that you can target different sized nodes, and also detect more container limits in response to those. We also want to finalize the API. So this means figuring out the things that the user might need and seeing what other things that we can do in the JVM to simplify this process. We're looking for more real-world applications to try this with. So we've done experiments with Liberty. We've done some preliminary experiments with Spring Boot as well. But we're looking for other types of use cases so we can, fully understand the space. Lastly, we want to make tools to make figuring out where to take checkpoints easier. So things that will guide users to determine the pros and cons of a certain position, how many fix ups are required if you take a checkpoint in one place versus another. And yeah, I think this concludes my presentation. So thanks. I think I'll take one question. Yeah, sure. Incremental, yeah, okay. Yeah, so incremental snapshots are not our #1 use case. Our primary focus is improving startup time. So this use case is a single snapshot. That being said, we have seen there are some use cases that do benefit from incremental snapshots. The challenge there is that the JVM has to be conservative the entire lifetime. We have to be conservative not just in performance, but also from a security perspective. We have to be very careful about what state lives for each increment. And so in the short term, it just means that you're fairly limited in some of the security services you can use this mode. But apart from that, it does work. You can use it. You can try it. I will say CRIU itself tends to be finicky about every time you restore, it tries to get the same thread IDs, same process IDs, and you have to be careful that sometimes the OS doesn't recycle them fast enough, and if the IDs you need aren't there, then the restore fails. So that's another thing you have to think about. Okay, so yeah, I'm over time, but if you have any more questions, please find me later. Thanks, everyone.